In this session, we are looking into the I2C protocols, FAQ, frequently asked questions like reason for missing acknowledge in I2C protocol, solving address conflict when sharing I2C bus, clock stretching, arbitration. I2C protocol, some real-time questions will be answered by these three, by getting into these three. So to get into all these things, we need to know get into the introduction of I2C protocol. So inter-integrated circuit, also called as I2C or I2C, is a two-wired protocol that can operate at different speeds: standard mode, medium speed. Although other protocols are simpler and do not have speed limitations such as SPI, serial peripheral interface, the scalability offered by I2C made it attractive as an interface for some of TI's, Texas Instruments CDC products. I'm just taking the case study of CDCs here. I2C prevents data corruption by performing a wired AND operation, as I2C interface has open drain or open collector output. When the SDA line is low, that is serial data line is low, that translates into I2C bus as being bus busy. Also, this interface allows the master to check the bus standards. By pulling the master data line high, it can verify the status of the bus busy if the line stays low, as some devices is pulling the line low, or free if the line is high. We dig deeper by getting into the protocol description. I2C protocol is generated by SDA, which is bidirectional line, receives I2C pattern and transmits them. It transmits the acknowledgement when a communication was successful. And SCL, that is clock line, one direction or unidirectional line. As I2C protocol allows multiple slave devices connected to a single I2C bus, each of them is identified with a different address. To address the slave devices, 7 bits are used. Transfers are initiated by start condition, that is when a data line in falling edge and clock line is high, and transfers end when a stop condition occurs, that is rising edge on data line while clock line is high. An instruction is sent through the SDA or in blocks of 1 byte, where the first bit is the most significant bit. SDA bits must best able while clock line is high, and they must change while the clock line is low. If SDA bits are not stable while SCL is high, it is understood as a stop or start condition, a typical cause for corrupted message or missing acknowledgement. The number of bytes transmitted is unlimited. Each byte must be followed by an acknowledgement bit from the slaves confirming the successful reception of the byte. Absence, the level remains high during the 9th SCL pulse. This is how the frame is associated with, and the various representations like start condition S and SR, repeated start condition, or read write, or 1 equals to read and 0 is write, acknowledgement, stop condition, and master slave transmission in this color and slave to master transmission in this color. Now the question, reason for missing acknowledge in I2C. First one is timing. Even when using a processors that generate two wired interface sequence, timing still must be checked. It is possible that the delay between clock and data is not complement or too marginal with the defined timing. In those cases, unwanted start or stop conditions can occur in the middle of I2C pattern, causing the slave to get a different message or resulting in missing acknowledgement. Second is missing or unexpected clock pulses. An unsuccessful execution occurs when a missing or unexpected clock pulses are within the protocol. If something unexpected happens, it is assured by the design that a start condition discards the previous incomplete or erroneous message and the device is ready to receive the new message. Incomplete. Third reason is incomplete 8-bit block. When less than 8 bits are sent, the slave waits for the rest of the data. Unless the 8th bit is sent, the slave does not generate an acknowledgement. A way to restart the transmission is starting new message with start condition to send the new I2C pattern. And next is missing bytes. This is very crucial. We'll take an example of CDCE 949, 937, 925 and 913. When a block operation is performed, the amount of bytes to be sent or received may already be fixed in another register. If the number of bytes sent or received is less than the number expected, the state machine waits for the rest of the message. The start condition can be patterned in order to skip the waiting state. When block read is patterned on these devices, B count located in the register address 08 hexer. Bit 7:1 sets the number of bytes that are read when performing a block read. A missing acknowledgement or misunderstood message can occur while performing a block read if the B count is set to greater value than the bytes available from the offset on the command code. Next is false slave address. Each I2C device is connected to the I2C bus has its own slave address and responds only that when an I2C protocol is being patterned. When the slave's devices identify itself with the address being broadcasted in the I2C bus, it ties the data signal to ground. For that reason, data is bidirectional, so that it can handle the acknowledgement received from the slave. And sixth reason might be is missing acknowledgement after changing the address. This quite often happens with this CDC 949, 937, 925, 913. During a write instruction block or byte, each byte change is effective when the last bit of the data is a byte. Data byte is patterned. After changing bits 1:0 from register address 01xh, the slave address changes. Therefore, the next I2C message starts with the new slave address. Using the old slave address causes a missing acknowledgement due to false slave address received. If during a block write 1:0 value of bits from register 01xh change, this translates into different slave addresses. But it does not impact the communication as the slave address is only checked in the first byte of the block write message. When programming via I2C, so for 906 and 706 slave address is 1101 0001. When a byte write is protected to set register's address at 10xh last bits to 1111, then A0 and A1 control pins overwrite last 2 bits of the slave's slave address. When A0 and A1 pins are left floating, the pulled up registers set their value to 1. After that byte write, the slave address is defined to 11010, A0 and A1. If the slave address in the next I2C message is not the new one, then missing acknowledgement occurs once again. If the last 2 bits of the slave address are set by A0 and A1 and the A0 and A1 pins change, it does not impact the communication as long as this change occurred after the first block of I2C message was patterned. If slave address changes during a block write, the communication is still successful as connection with the device was already established during the first block of the I2C message. So how to solve a address conflict while sharing in the I2C bus? A conflict occurs when more than one devices having the same slave addresses is connected to the same I2C bus. In 949, 937, 925, in 913 belong to the as they all belong to the same family, the same performance but different outputs. Their slave address has one part fixed or hardwired, and one part programmable. So this is an advantage. With 941 and 937 share the same hardwired address, the same situation applies to the 925 and 913. For this reason, we can go up with the branching of it actually. If slave reason address programmable part changes within each of the defined groups, it is possible to reprogram them to have the same slave address. That is, 949 can be programmed to have same address as of the 937. But in this situation, when connected to the same I2C bus, a conflict arises. So there is a possibility of reprogramming we can reprogram the last 2 bits of their default slave address. Therefore, up to 4 devices of each can be plugged into the I2C bus. Each of these devices default setups are set to have different slave addresses. Therefore, with the default setup, one of each of them has to be able to share the same I2C bus with no conflict. Some devices offer possibility to fix the slave address with control signals. Thus, the same device can override itself its slave address with control pins, that is last 2 pins, and it is unnecessary to pre-program the device. So 906 and 706 offer the possibility to override the last 2 bits of their slave address with external pins 1 and 2. One will have multiple pins multi-functionality S0, A0, clock select, and 2 has S1, A1 are shared with the other functionalities. These pins act as a A0 and A1 when setting the 4 lower bits of the internal register 10xH to 1111xB, that is binary. When A1 and A2 are left floating, the effective slave address is 11, as each of them has internal pull-ups of 150 kilo ohms. If the slave device has fixed address, or if the preceding options are not preferred, then an I2C multiplexer or I2C buffer can be used. So I2C multiplexer splits the I2C bus into several sub branches and allow I2C master to select and address one of the multiple identical devices, thus resolving the address conflict. That is, the key here is sub branching it, as mentioned above. The multiplexer connects the main I2C bus to the selected slave device and removes electrically the non-selected devices. That is what that 150 kilo ohms will do after we implement this. This device is programmable via I2C protocol. Therefore, no additional pins or control logics are required. Texas Instruments PCA9544A can multiplex up to 4 slave devices with the same slave addresses. So here is multiplexing is the key to solve the conflicts, address conflict. So if I2C buffer is chosen, then additional lines and optional control logic is needed to enable or disable the I2C bus branch corresponding to the addressed or non-addressed slaves. Now the final is clock stretching. We will learn about clock stretching and arbitration. Before that, we need to know what is a clock generation. When clock is always generated, the clock is always generated by I2C master. The specification requires minimum period for the low and high phases of the clock signal. Hence, the actual rate may be lower than the nominal clock rate. Example, I2C bus with large rise times due to high capacitance. So clock stretching, that means slowing down the communication by stretching SCL line. During an SCL low phase, any I2C device on the bus may additionally hold down SCL to prevent it to rise high, again enabling them to slow down the clock rate or to stop I2C communication for a while. This is also referred as clock synchronization, which is a good technique, right? And then The major note in that particular process is specification does not specify any timeout conditions for clock switching. That is, any device can hold down SCL as long as it likes. So coming to the arbitration, this solves many things, like when I2C multi-master bus, multi-master can be connected to the same I2C bus and operate concurrently by constantly monitoring SDA and SCL for start and stop conditions. They can determine whether the bus is currently idle or not. If it is busy, masters delay pending I2C transfer until a stop condition that the bus is free again. However, it may happen that two masters start a transfer at the same time. During transfer, masters constantly monitor SDA and SCL. If one of them detects that SDA is low when it should actually be high, it assumes that the another master is active and immediately stops its transfer. This process is called arbitration. Arbitration will solve this multi-master connection and operating concurrently conflicts. So we could able to answer these questions during your interview times or whatever it is. Now by this time you understood what is a bus arbitration, what is clock stretching, what is the reason for missing acknowledgement. We discussed 6 reasons over there. What is the data validity, what are the different speeds of I2C protocol, why did you choose this protocol, what is the default speed of I2C protocol. Hope you understood this, and wait for the FAQs 2 onto the this thing. Thank you.